All right, so to end the last video, I kind of talked about what would happen maybe if we were to shift this signal down to where the high value was at VH over 2 and the low value was at minus VH over 2, and the signal would swing around 0. I'm sure you probably know, but in case you don't, what would basically happen is, let me actually just duplicate this slide. Might as well make another one. If we had that case, we would have something that looks like this. Blah, 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 blah. We'll call this T over 2 and this time T. And we'll say this is VH over 2 and this is minus VH over 2. And basically what's going to happen is we're going to try and take the average of this signal. We'll call it Vx2 of T. Vx2 average is going to be equal to 1 over T times the integral from 0 to T over 2 of VH over 2 dt plus the integral from T over 2 to T of minus VH over 2 dt. And because these two integrals are really just areas, we can just kind of do this by inspection, or we could do it mathematically. But what's going to happen is we're going to get this positive area is going to be some value. What is it going to be? It's going to be VH over 2 times T over 2. And this minus this second area here is going to be minus VH over 2 times T over 2, because it's just T minus T over 2, right? That's the distance here. We're taking the areas. And since the areas cancel, this entire integral is going to go to 0. And if that's the case, that means that the average value of Vx2 is 0. And that's interesting, because if we're going to do some calculations where we want to multiply the average value of our signal by something, we're just going to get 0. And for power analysis, that's not okay, because a lot of the times our signals do oscillate around a value of 0. Sine waves in particular will do the exact same thing, because any time that the positive area and the negative area are going to cancel each other, like this, if I had T over 2 here and T here, obviously the computation would be a little bit more rigorous because of the sine wave. But nonetheless, we have a positive and a negative area equal in size that are going to cancel. And so the average value here, sorry, I don't know what kind of arrow I think I'm drawing there. The average value here would be 0 as well. And so this is something that we have to deal with in electrical engineering, because we don't want this average value to be 0 when we're doing computations. So this is where the RMS value comes into play. There are two sort of ways to think about the RMS value. Based on what I've been saying up to this point, we should look at the second definition first, which says that the RMS value can be thought of a meaningful average for a signal whose actual average value is 0. Okay, so a signal like a square wave or a sine wave that swings around 0, just like this, does not have a 0 RMS value. It has a 0 average value, but it does not have a 0 RMS value. So let's take a look, and then I guess the second definition here is the RMS value is a DC value. So when we calculate the RMS, there will be no more dependency on time. It's just going to be a theoretical DC value. It's not an actual, DC source or anything like that, but it's DC mathematically, in the sense that it doesn't change with respect to time, okay? So the DC value that delivers the same average power to the load as the original signal. Okay, so what that means is, if I have a circuit here, sorry, I should make this sinusoidal. If I have a circuit here with some sinusoidal source V1 of t, and I have a load here, we haven't talked about power yet, but this source, even if the signal is swinging around 0, swinging around 0 like this, its average value may be 0, but it's still going to deliver some average power to this source. So this source dissipates P average. Okay. Now, the RMS value is a DC value. Note that this is not a DC value, right? This is a sinusoidal source with dependency on T. If I take the RMS value of that source, which we're going to look at the formula in a second, but I haven't talked about it yet. If I take the RMS value of that source and I were to connect a DC voltage source with that RMS voltage to the same load, I guess I should call this load ZL, and then this is also ZL, they would have the same average power, okay? This sinusoidal source and this DC source with the RMS value of my original signal would have the same average power into the same load. That's the first definition there. That one's not as relevant just yet because we haven't talked about power and all that, so it might be confusing. So for the time being, you can think of the RMS value as a meaningful average for a signal whose actual average value is 0. Okay? And so in the next couple videos, I'm going to show you how to implement this formula, but for now, let's just talk about what this formula is actually saying. So RMS stands for something. Obviously, I hope you didn't think it was just 3 random letters. RMS stands for root mean square value. And you may be like, what in the world does that mean? But if you look at the formula and we kind of break it down, it'll make perfect sense what that means. And so let's take a look at this formula. Imagine I have a signal here, x of t. And again, my signal has an average value of 0. Well, what happens if I square my signal? So if I take x squared of t, x squared of t would look something like this maybe. Right? So now my signal doesn't have a 0 average. It would have some non-zero average. It would be an average somewhere up here, right? Where my original signal did have a 0 average. It was going right through the x-axis. Okay? So now my signal that I squared, it has a non-zero average. But now my signal is much larger than my original signal. So if I were to square root it, I could bring the signal back down to some new value, something like this. I guess from that point, once I've squared it and taken the average, it's just this thing that I'm square rooting. It's the average value that I'm square rooting. And then if I square root that, it would pull it back down maybe to here once I take the square root of it. And so basically that is what the RMS formula does. It takes my original signal, my x of t, which has a 0 average, right? It squares it to get rid of the negative part so that I can get some kind of an average that's not 0. But then that average is too big because I squared my signal. So my signal got, not only did it get, flipped up to the positive axis, but it also got squared. So it's too big. So once I get this average, I square root that to bring it back down. And that final value, that is my RMS value, okay? So that might be confusing, but that is why this formula is called the root mean square formula or the RMS formula. It is literally the root of the mean or the average. If you notice, this is just the formula for the average that we just saw, 1 over t from 0 to t dt. But it's not x of t, it's x squared of t, right? That's the square. So it's the root of the mean of the square. That is what RMS means, okay? So this might be confusing, but I think it'll make some more sense after we do some examples. So in the next couple of videos, I am going to solve for the RMS value of a couple different types of signals so that you can see what the process looks like for finding the RMS value, okay? So I'm gonna go ahead and end this video right here.